okay. It really is okay that you're tired. You know why you guys are tired? You've been working really hard for a really long time. This is how it happens. You get tired because you worked hard, and you deserve to be a little bit tired. You don't deserve to give up. You deserve to push a little bit harder for a little bit longer. Tuesday, May 9th is going to come. Now, because I want to look out for Mr. Garcia, Wednesday, May 10th is going to come. And is Wednesday, May 10th the last one?
Yes.
That's it. You're done. After that, long live senioritis. Long live bad decisions being made by teenagers during the school day. Okay, so every summer I get the pleasure of working with about 60 math teachers in New York City, and I push them, push them, push them. They are with me in a room every single day from 9 a.m. to 6 p.m. for 2 weeks. That was the noise of like, ooh, how lucky for them, I know. I get to teach Algebra 1, Geometry, Algebra 2, Pre-Calc, Trig, Statistics, Probability, and a little bit of Calculus, and then a little bit of non-Euclidean Geometry over the course of 2 weeks. 9 hours a day, don't worry about it. And about this time, they get way tired. And so at about this time, I ask them to humor me, and I say, go up against the wall, find a wall. Find a wall. Go find a wall. Go find a wall. A wall, not a bookshelf. Okay. And Sidney Poitier, who is one of the most amazing actors ever, but he's so old, most of you probably don't know who he is. He did some amazing movies. He's an amazing, gifted actor. He took on some of the most challenging roles. He's an African-American actor in a time where African-American actors, there were not a lot of them. And so he had tough stuff to do as well. And so what he would do before he would get into a role, he would try to do something really hard as well. And this is what we're going to do. He would actually start, before he went into the interview, he would find a wall. Kids at home, find a wall, a really strong wall. What you're going to do is you're going to push, you're going to knock the wall down. You're going to knock the wall down. Maybe you could go somewhere else. Your job is to knock this wall down. Just push as hard as you can. Push. Push it. Not the door, fool. The wall. And just push.
Not the fire alarm either.
Push. Push that wall down. Now, when I really get pushy, I get stronger when I make a noise. Make an appropriate noise. It'll help you push the wall down. Push. Everybody get back to it. Yeah. And for some of you that had your other noises because you were pushing so hard, you know, hey, life happens. Anybody feel a little bit better? Okay, arms tired. We needed to do it quickly because I'm sure Miss Ogden is like, what the hell is going on next door now? We're just pushing. It really helps me to feel better. There are times I have gone out to the backyard and I push on the tree. There are times I have taken the baseball bat with me to the tree. For the trees, okay. All right, so let's talk about life the next couple of days. There's a lot going on. How many of you are not going to be here on Monday because of the APES exam? Okay, that's right. We already did this the other day. Who is going to be here on Monday? Okay, Stephen's so busy, he's like, I don't have time to raise my hand. I'm pushing, knocking a wall down. So the three of you and you, we are going to keep going with advanced integration techniques. Nothing new, it'll be a review day. It'll be an opportunity for some practice, okay? Friends that aren't going to be here, your job, watch the video. Okay? All right, I've got a quiz for you. You knew it was coming. It is a take-home quiz. 1, 2, 3, 4, 5. Hold on. Okay. Okay, please, before you do something foolish, write yourself a little note on the bottom that says, turn me over. There's 4 more in the back. Louis, like, oh my God, I wouldn't have known. I know, son, you wouldn't have known. Okay, so there are 4 on the front. There are 4 on the back. Some of these, you know what's not really on here? Is partial fraction decomposition. Okay, bummer. It's going to be okay. Okay, I am not going to pick this up as a quiz grade. These are just practice problems for you to do this weekend. For anyone who is taking the APES exam, stay with me. It is an optional assignment that you don't have to do. You missed it, but I will show you later. Anyway, so this is an optional assignment for anybody who is in APES. For anybody who is in APES, who does this assignment this week and who leaves it in my mailbox Monday morning, it is a free 100 on a homework assignment as long as you do all 8 problems. Everybody good? Palamon? Those of you that aren't in APES have the time this weekend to spend the time to do this well.
Can you get 100?
Let's see what you do. All right, but for the APES folks, if you don't get a chance to do it, I completely understand. I'm just going to mark it as excused because Ms. Hanlon is a good friend of mine and I want you guys to really be set up for success for the APES exam so you can get that over and focus exclusively on mine. All right, so there's that. Now, once your APES exam life is over, now that brings us to the next thing. 1 for you, 2, 3, 4, 5, 6, 7, 8. Stephen, don't start doing these yet. I know you've been tempted. Don't do it. 9, 10. Okay. This is the packet for the next unit. And you're like, well, wait, what unit? The review unit. The review unit being 6 days. Okay. What these are, I started doing these last year, and I think it was one of the smartest things that I did last year. And let me tell you, I do a lot of smart things. Just like Professor Dumbledore. So 3-a-days. The AB kids do 2-a-days, but that's AB. 3-a-days. 3-a-days are 3 free response questions that you're going to get every single day for homework. Every single day. No. I choose them. So on Monday, your homework is to do 3-a-day, day 1. Right? Oh. So that's why I wanted the APES friends to get this now. The homework that is due Monday is optional for the APES friends, but this is required. Tuesday. This is the homework you guys are going to get on Monday, but I can't email this to you, and I didn't want to email it to you. Thank you, Mr. Lake. Okay. What's going to happen with each of these 3-a-day problems, there's 3 problems. The first one, take a look at it. Although it's long, and there's a lot of reading here, it's a rate functions question. It is an AB rate functions question. The second question is always going to be a BC topic. This one's going to involve advanced integration techniques. Oh, how convenient, we're doing advanced integration techniques. And then there's one more. Series. Every single day for those last 6 or 7 days, you're going to do a series question at night for homework every single night. It's going to take you about 1 hour to do this, to do it actually really well. My goal is to be available for as many lunchtime sessions as possible next week so that you can come and get some support and we'll do all the things. The only thing that'll trump that is if I find out that I need to be gone because, you know, like, oh, there's like second child coming and I need to go take care of business. Everybody good? Okay. So with that said, that's the quiz, which is really sort of an optional thing. If you're doing APES, there's the 3-a-day, day 1. We talked about the APES exam. David, we're going to talk in a little bit. Okay, room 18. On Tuesday, I'll put a note up on the board on the door. Tuesday, this room is off limits because I think this is where AP Spanish is happening. Some exam is happening here on Tuesday. So we're going to be in room 18 instead on Tuesday. Next, 17 and 19. Yeah. Okay, and last thing, MFA scholarship. You guys got the email last night that basically said my door is closed. If, however, I have already written a letter of recommendation for you and you want me to serve as a recommender, I'm more than happy to do that. But only if I've already written one for you. Because then I'm just going to pick out a paragraph or 2 and say, here's my submission. I'm not offering this to the AQR friends. Does anybody in here need me to do that? No? Good. Moving on. All right. If there's time, we'll do the homework at the end of the period. All right. This is sad face. We're about to start the last thing. No, Myra. Myra, no, you're the good girl. Oh, no. You're the good girl in the room. I expect these things from LA. Okay. Or maybe not. Maybe it's just dumb. Okay. Seriously, this is it. I have nothing left. Not nothing left that I know. Nothing left to cover in the BC curriculum. This is our last topic. Hallelujah. Praise Jesus. We have made it. This time last year, there were 2 rain days, which you guys were really excited about, and all the calculus teachers were like, ah! The topic is improper integrals, and I want to just kind of talk about integrals. Right now, in your world, you know that there are 2 kinds of integrals. There are 2 flavors of integrals that we've dabbled with this year. What are they? There's definite and the indefinite integrals. And so in the world of a definite integral, I mean, you guys know at this point, a definite integral just looks something like this guy here, the integral from a to b of f of x dx, right? Okay. And then we've got the indefinite integrals. And an indefinite integral or an antiderivative indefinite integral looks something like that. And I know for the 10 of you and everyone watching at home, we are super clear on the difference between a definite integral and an indefinite integral. Okay, good. Well, in the world of definite integrals, there's a split, there's a further split to what we are going to call a proper integral and an improper integral. Improper integral. A proper integral has to satisfy these 3 conditions. Pretty much every integral we've seen so far has satisfied these conditions. What you need to be doing is you have to have a continuous function, and you have to be on a closed interval, and I think as I play back the footage in my head, I said there's 3 conditions, there's 2. You're integrating a continuous function over a closed interval. All the graphs are always going to look something. Here's f of x, here's x equals a, here's x equals b. That's the area that we're looking for. Everybody's good with proper integrals? Improper integrals means one of these 2 conditions is missing. Either one is missing. So maybe what you have is a closed interval, but you have a function that's not continuous. Maybe what you have is a continuous function, but you don't have a closed interval. Okay? If either of these 2 conditions is missing, that forces us into the land of the improper integral. Improper integrals are going to do one of 2 things. They're either going to converge, which you guys know means what? Converge. Approaches a number. Approaches a finite number. Or the other option? They're going to diverge. They're going to go to either a positive infinity or they're going to go to negative infinity. Converge means you're getting closer to a finite number. Is everyone mostly good? Okay. Improper integral just means one of these 2 really important conditions isn't there. So for example, Stephen, if I'm over here, can people see? Yep. Okay, integral of 1 over x dx. Talk to somebody near you. The integral from 1 to 4. Proper or improper and why? Proper or improper and why? How many guys are proper? I see 3. How many guys are improper? How many guys have no idea? Be honest.
Oh, sorry.
Proper. In order to be a proper integral, 2 conditions. Function has to be continuous on a closed interval. Do we have both conditions? Right. 1 over x is not a continuous function, but on the interval 1 to 4, it is a continuous function, so this is proper. Yay. Okay, how about the integral of 1 over x dx from negative 1 to 4?
Improper.
Improper? Lewis, why improper?
Because from negative 1. Because there is nothing.
Improper because not continuous. Continuous at x equals 0. Everybody okay? All right, integral of e to the x dx from 0 to infinity.
Improper.
Improper? Why improper?
Infinity is too big. It's like you can't actually tell.
Right, you're going to infinity. Imagine the graph of e to the x. Like here's the graph of e to the x, and you're saying start at x equals 0 and go until when? Infinity. Forever and ever and ever. This guy is improper, and I'd say because the upper limit is infinity. We're good at improper. Converge or diverge? Don't overthink it. Diverge. Why diverge?
Because it's not approaching one number, it just keeps increasing.
Right? I'm saying find the integral from 0 out to forever. This guy here must diverge. And you could even say just by inspection diverges to positive infinity. This is okay. Big picture, proper, improper. Now, we dabbled with some improper integrals before, and I said, hey, don't really worry about it. We're just going to like handle it. Today is when we're actually going to handle it in a proper kind of way. All the definitions are going to be in a proper, maybe use a British accent if necessary, proper way. There's where my rag is. Turn it into a placemat. All right, so take a minute. I want you to read through this first definition of an improper integral, and then we're going to talk. I'll take attendance. Palamon, you might want to move so you have somebody you can talk to.
I never talked to them.
Okay, fine. Doesn't sound like much reading. F is continuous on the interval a comma b. Closed at a, open at b. And f of x approaches infinity, or f of x approaches negative infinity, as x approaches b from the left. We define the improper integral of f on the interval ab by this guy here is equal to the limit as r approaches b from the left. R is like the new thing here. The way that we handle an improper integral is we make it look, I want to get this part across the plate, we make it look and feel like a proper integral. Okay? So let's look at one of these. What? So if I want to find the integral from a to b of f of x dx, but the function is not continuous at the endpoint, what we're going to do is we're going to pick a value of r and we're going to say find the integral from a to r of f of x dx and take the limit as r approaches b from the left. Okay? And we're going to go from there. So here's what we know. We've got some function, just a nice little picture to draw here. We've got some function f of x. Here's f of x. From x equals a to x equals b. All the friends are okay? What I'm asking you guys to find is the integral from a to b of f of x dx. And this is an improper integral because?
It's not on the closed interval.
You lost me at it.
The function.
The function is not continuous on a closed interval. Okay, what we have here is a vertical asymptote at x equals b. The way that we're going to handle this, so vertical asymptote at x equals b, is we're going to draw a line at some other place that we're going to say x equals r. And what I want is I want to find the area from a to r. So instead of going from a to b, we're going to say find the area from a to r of f of x dx. Is that proper or improper?
Proper.
Right, proper, because the function is continuous on this closed interval. But I don't think any of you are going to be fooled into saying, oh, the area here is the same as the area here. This is going to be a place where we actually bring in limits. I know that from a to r, I have a proper integral because I have a continuous function on a closed interval. What if I move r a little bit? Still proper? Move it a little bit? How far can I move this guy to the right and still be proper? If my discontinuity happens at x equals b, I can go as far as I want to. I can get way close. I can get limit close. And so what we would say is that the integral from a to b is equal to the limit as x approaches r from the left of the integral from a to r of f of x dx. X equals r is this extra line that you're drawing so that you have a proper integral, and the limits just say push it. In the words of Salt and Pepper, push it good. Just push it, push it, push it, push it, push it, push it as close as you can get to x equals b, but don't ever actually get there. Get limit close. Look, those.
Does this also work with A?
And this absolutely, there's nothing special about b. Maybe what you have is a function that is continuous on an open interval. You can push in both directions. Okay? All right, so let's look at this first example. Identify why the integral, the definite integral from -1 to 0, 1 over x squared dx is an improper interval. Improper. Improper because? Because 1 over x squared is not continuous. Well, let's be specific.
At X equals 0.
It's not continuous at x equals 0. Okay? So what we're going to do is we're going to say, all right, well maybe you want to even get a little graph, and I'm picking friendly functions. 1 over x squared looks something like that guy there. And I need to integrate from -1 to 0. 0 is where we have the problem. To find the integral from -1 to 0 of 1 over x squared dx, we're going to say draw in that extra line. And there's really nothing magic about calling it R. You could call it B, you could call it A, call it whatever you want. But I picked R because we don't normally use R. So we're going to rewrite this and we're going to say, okay, it's the limit as x approaches what? We've got to be way careful here. Oh wait, I just can't believe I just did that. It's not the limit as x approaches R. It's the limit as R approaches 0. In fact, go back in the notes. It's going to be the limit as R, I can't believe I did that. R approaches B. Right, you want this line that you just drew to get closer to B. Sorry about that. And we're going to do an integral from -1 to R of 1 over x squared dx. Proper or improper?
Proper.
If you're going to go from -1 to R, this is proper. Because it's proper, good news, you can integrate it in the way that you always integrate things, carefully, so like finish it off. The only new piece is what we're going to have to do at the end. Integral of 1 over x squared. 1 over x squared, that's really x to the -2 power. Add 1 to the power, divide by the new power. The antiderivative is -1 over x. You're evaluating from -1 to R. This guy's your antiderivative. We're going to evaluate. Okay, do the evaluate. Limit as R approaches 0 from the left of -1 over R minus -1 over -1. Need the limit as R approaches 0 from the left of -1 over R minus 1. What's the limit as R approaches 0 from the left? Be careful. I like ending with this because it brings integrals all the way back around to limits. R gets close to 0. It means R gets small. What happens as R gets closer and closer and closer to 0? All right, if you're not sure, do what we used to do way back in the day. Pick a small number. Pick a small negative number, like -0.001. -1 divided by -0.001, guess what? -1 divided by a small negative number. It's big. Big positive or big negative?
Positive.
Uh-oh, big positive or big negative? Go back to your limits here. R gets close to 0 from the left, for example, -0.001. -1 divided by that negative number is a big positive number. Then I'm going to subtract 1 from that, so what? You're going to get a big positive number. The limit is infinity, so what you would say is, does it converge or diverge? It's going to diverge. So, diverge. Other friends mostly okay with this idea? The big thing, the big takeaway is that when it comes to improper integrals, you make it a proper integral somehow, and usually it's going to involve limits. All right, so if you guys are good with this one, I want you to just take a little bit to read over the introduction to number 2. We're not actually going to do number 2. I just want you to give it a read. We'll take a look at it, and then we're going to spend the rest of the time on the important improper integrals. Is continuous on the closed interval a, b, except at some value c. And f of x approaches infinity, or f of x approaches negative infinity, as x approaches c. We define the improper integral of f in this particular way. So what's the visual? I think if you can get the graph in front of you, life's not too bad. What do we know about f? Continuous everywhere?
Except at x.
Except at x equals c. So whenever you're going to draw here, you need a function and you say, okay, here's x equals a, here's x equals b. You've got to draw some function, but you've got to draw it in just the right way here. It has to be continuous everywhere except at c, where c is some number in between. I don't care what c is, but it's somewhere in between. It's the type of discontinuity that's important here. What we know is that it says, and f of x approaches infinity, or f of x approaches negative infinity as x approaches c. You're getting closer and closer and closer to c, and the y values are approaching infinity. So maybe what you're thinking about is like another vertical asymptote, but this time you've got a vertical asymptote inside the interval, not at the endpoints. And your function maybe does something like that. This is the case. What I want is what's the area from A to B. Let's take a little bit of time, look over this again, get your head straight with this. Go back to their definition. Look at how they're defining this. So we're looking at this bad boy here. We've got two different pieces, right? If we're going to make it proper, we have to do this in such a way that this piece over here is proper and this piece over here is proper. And so what we're going to do is we're just going to say, draw another line. Let's call this x equals r again, whatever. And the integral that is going to get this guy is we're going to say it's the limit as, I'm not going to make that mistake again. We're integrating from a to r. We're integrating f of x, but what's the limit? The limit is what happens here. Here's x equals r. What are we doing for this first integral? R approaches c, but be careful, from the left. So it's the limit as r approaches c from the left. This is going to give you the area for region number 1. That's not the total area, because now you need to go over here and look at region number 2. Thoughts over here? David, what do you want to do?
If we're doing like the same thing, we'll do we'll set it up that the limit integration will be from C from R to another R.
Right, and here's where you need to be careful. Don't use R again. We are already using R on this side.
And let's use that, the subscript.
Right, if you want to use subscripts like R sub 1 and R sub 2, maybe you're like, hey, you know what, we haven't used, I don't know, x equals D whatever, it doesn't really matter. And now we're going to say, oh, so now I need a limit. I'm going to do the integral from, what is this, d to b, f of x dx, and all I need now is like, what's the right limit way to express this? Lewis, what do you got for me?
As d approaches c from the right.
The limit as the d value, I'm pushing. Oh my god, the whole Sidney Poitier push the wall thing totally connects here. It really is. I'm even smarter than I thought. In that saying something. It's the limit, it's the limit as d approaches c from the right. That's what happens when you say you're so smart. And this gives you area number 2. And we're going to add these together. Ready to go? Okay, what if the first integral converges and the second integral converges?
They both converge.
That's another way to say they both converge. The first one
The whole
converges.
thing converges.
The second one converges. The whole thing converges. First one diverges.
All of these.
Second one diverges. The whole thing diverges. First one diverges. Second one converges. Whole thing diverges. If any piece diverges, whole thing diverges. Exactly. The other one's irrelevant. All right, cool. Let's keep going. Keep going. All right. Give yourself a little bit of time to read, and then we're going to work it. Get your head straight with this one. So sad. This is the last new thing.
Yeah.
Until after the AP exam.
Oh, and then we can do the color thing where it's like, if it has a 2 in it, you color it green.
Nah, it'll be like the first grade.
We're going to do some coloring.
It'll be like
I really
1
hope
plus
that.
1.
If you make us color like a sign or
reals.
something, I'm gonna
Bro,
For reals. For reals, we have a coloring day.
I've been
All right, shut up and read.
No. 2 grade.
David, you missed the shut up part.
I was missing.
No. F is continuous on the interval a to infinity. This is an improper integral. And the integral from a to infinity is the limit as r approaches infinity, a to r. Everybody kind of okay with this one? Right? So the picture you've got is you've got some function. Here's x equals a. We've already looked at one like this. Here's f of x. And the area that we want is the area from a to infinity. We're not going to do that. We're going to introduce this other line that we're going to call x equals r. And we're going to say, well, really what I'm going to do so that I get all the points on the exam is I'm going to find the integral from a to r, which is proper, continuous function, closed interval. And then it's just going to be a matter of limit as big R approaches infinity. Okay. So, with that said, if you're feeling really comfortable with yourself and all this stuff, then give it a whirl. Cosine of x, e to the negative sine of x dx. If you're feeling good, go solo. Show me what you can do. Integral from 0 to infinity, cosine of x, e to the negative sine of x. Back when we were in the series unit, I just said, let's not worry about it. I waved my hands a little bit and I said it's an improper integral. Is everybody okay? This is clearly improper. Improper because we're going to infinity. It could be doubly improper. Do we have a continuous function? Cosine of x, continuous. E to a power, continuous. Whole thing multiplied together, continuous, thank God. Okay? What makes it improper is the infinity, and so really I'm just interested in my first pass, even if you don't know what the graph looks like, can you set this up so it looks and feels like a proper integral? The only thing that makes it improper is the infinity, so we say do an integral from 0 to r of cosine of x, e to the negative sine of x dx, and take the limit as r approaches infinity. I would suspect that's probably going to get you in the door and you're going to get the first point. Like, for real, that's where we are. Okay, now you get to integrate it. actually have to integrate. Cosine of x e to the negative sine of x. Need to integrate. Options that are running through my head right now. The partial fraction decomposition. Of course not, there's no fraction. Integration by parts, right? We've got a multiplication thing going on. How about substitution? If you're going to use substitution, what's the u? Your best guess for the u, right? The baby likes to hide in the exponent. So u is negative sine of x.
U is.
U is. du is going to be, what is that? Negative cosine of x dx. Hey, good news. Good news happening here. This is what we expected to happen. Okay? So now let's do the substitution. We're going to do an integral. Instead of cosine of x e to the negative sine of x dx, I need negative of this. So it's the negative of du instead of e to the negative sine of x, e to the u. Now you got to be careful. You really have to be careful. You all have been raised well on a diet of really good notation. When you do substitution, you don't just change the integrand. You have to change the limits. Right? The limits used to be x equals 0 and x equals r. Now they're u's. So if u equals negative sine of x, then that means that the lower limit is 0. The upper limit is x equals r, so the u value there is negative sine of r. Take the limit as big R approaches infinity. The integral, I know that's ugly, don't sweat it. The integral of negative e to the u, everybody needs to know. Not e to the u, but the negative of e to the u. Right, so we've got here negative e to the u. I want to be careful with my notation. We're integrating from 0 to negative sine of r. And we're taking the limit as big R approaches infinity. Well, let's plug everything in. This is going to be limit big R approaches infinity, negative e to the negative sine of r minus negative e to the 0. I'm starting to worry a little bit. I want to stop and look this one up just for a second. I worked through this. I think I may have been having a brain fart this morning. There's something I don't like, and I wonder if anybody else sees it. Okay. Are all the friends okay getting here? Okay. What's the problem? Take the limit as r approaches infinity. What happens?
Indeterminate form.
An indeterminate form where?
Oh my god, never.
The indeterminate forms are 0 over 0, 1 to the infinity power, 0 times infinity. It's not an indeterminate form, that's the problem. I can't believe I did this to us on our very first problem. This is not what I wanted to do. Andrew, what do you see? I saw you do something. What's happening? There's oscillation happening. So what happens as you take the limit as r approaches infinity, this part over here oscillates. It bounces between -1 and +1. So what happens is that this guy over here, I can't believe I missed that. This guy over here oscillates. If this is oscillating, that means limit doesn't exist. E to a power that doesn't exist, doesn't exist. So the whole thing does not exist. Does not exist because of oscillation, and when I think about doing this again next year, I absolutely want to change this problem. You guys are ready for this, but this is not the way I wanted to like open up the doors and say, fly birdies. Sorry. I like threw you guys into a fan. But big picture, are all the friends okay? We got this? Alright, so you can do this section. This is going to be our last. We're going to stop at this point. Why is this guy improper? We're going to infinity in both directions. This one is so improper. So improper. So you've got some function f of x. Now f of x is continuous. Maybe the graph looks something like that. I don't know. This is f of x. But what we're trying to do is we're trying to find the entire area from negative infinity to infinity. And what you need to do is make it look proper so that you can work with this. How are we going to make this proper?
Separate.
You want to separate it? How so?
From negative infinity to some.
So I hear you say let's do an integral from negative infinity until some place, right? Where? At A. What if I do it here at x equals 0? Would that be okay? What if I decide to do it out here at x equals 2? Would that be okay? It could be anywhere. So let's say, like, I'm going to say negative infinity to 0, but really it could be negative infinity to any number. And then I bet some of you would say, oh, and then easy, we're just going to do this guy over here. Okay. Not good enough. You still don't have a proper integral showing up. Lewis, why don't we have a proper integral showing up here? You still have infinity. You took your problem that was improper in both directions and you said, okay, I'm going to fix it. But you're going to fix it by splitting it, but now you're like, I have a starting point and I have no end point. So what we're going to do is we're going to say, okay, turn this into something and say, like, here, whoop, here, but I caught it, so that's good. Here's x equals r. And for this guy, we're going to say, let's do an integral from 0 to r of f of x dx and take the limit as r approaches infinity. Proper, push it. This guy over here needs to be proper, and we need to push, but we need to push in the other direction. So we're going to say this guy here, maybe you want to go like s to 0 of f of x dx, and it's the limit as s approaches negative infinity, and then add the two together. This is how we're going to play the game. Proper integral? Proper integral? So this is good. This like fits our description of what a proper integral should look like. We just have to use some fancy notation. Now, some textbooks are going to do this, and I don't like this approach, and I would never recommend you do this. Some textbooks say, well, if I'm going to use this place x equals r, how about drawing another line at x equals negative r? And they do an integral from negative r to r. Would that be proper? Go from negative r to r. Proper. And then what? We're going from negative r to r, but we need to go from negative infinity to infinity. You move, right? But you're moving them in a very like symmetric kind of balanced kind of way. You're saying like r gets big and they move away at the same rate. And no matter where you stop, you're still proper. The problem is sometimes when you do that, you get some weird things that start to happen that, anyway, it's just because you're moving them at the same time. If you move them separately, you say, let this guy go to negative infinity, find an answer. Let me move this guy, go to positive infinity, get an answer. Then that's okay. So with that said, see what you can do with this next one. I'm curious first and foremost about the setup, and then we'll evaluate it and close up shop for today. Mr. Link, we're doing functional analysis day 2, right?
Yeah.
Are they gonna start with some survival guide time?
Yeah, it's gonna be like 2 minutes of that, and then I think I want to do one multiple choice first,
Uh-huh.
and then coming up with a free response.
So that'll give me a couple minutes.
Yeah. And we did like practice it one, and then we'll do multiple choice. That's it.
So integral from negative infinity to infinity, x equals negative squared dx. I'm going to split this, so I'm going to say integrate to 0. And then start integrating at 0. Call this guy R, it doesn't really matter. Limit as R approaches negative infinity. I'm going to go to S, limit as S approaches positive infinity. Is everybody okay with this setup? Setup's feeling good and comfortable? Honestly, I'm going to call like today a success if everybody is really like, I've got this. I can take improper integrals and rewrite them as proper integrals. Huge points. Huge points coming. And now from here, it's just a matter of like, do you know how to integrate? Do you know how to integrate x times e to the negative x squared? X times e to the negative x squared, I think this is a substitution kind of problem. How many guys are pretty sure like you can do the substitution in your head? You just know what it is. Not there. I'm always curious because you all evolve in very different rates. If it's substitution, what's the u?
Negative x squared.
Negative x squared is going to be a good guess. Du, negative 2x dx, so negative a half of du is x dx. In my rewrite process, I've got e to the u. Instead of x dx, that's my negative 1/2 du. And I'm integrating. Let's get the limits of integration correct here, though. U is equal to negative x squared. If x is equal to r, then u is negative. Negative r squared, can't get enough of that. And if x is 0, then your upper limit is 0. And we take the limit as r approaches negative infinity. Hey, good news. This guy over here integrates the same way. It's the same integrand. I don't know that I'd redo any of the work. I'll just say it's negative a half e to the u du. And I'm integrating limits of integration now. Is that what, 0 to negative r squared? Negative s squared maybe? Limit as s approaches infinity. Integral of negative 1/2 e to the u is negative 1/2 e to the u. Negative a half e to the u from negative r squared to 0. Take that limit as r approaches negative infinity. Integral over here, negative 1/2 e to the u. Integrate from 0 to negative s squared. Take the limit as s approaches infinity. Add the two together. I'm assuming that for most of you guys getting here is okay. Just going to be careful with the notation. There's a lot of moving pieces. Okay, let's do the evaluation. Limit as r approaches negative infinity of negative a half e to the 0. Well, that's just negative a half minus negative a half, so that's really plus 1/2 e to the negative r squared. Plus, take the limit as s approaches infinity. Plug in the negative s squared, negative 1/2 e to the negative s squared, minus negative a half e to the 0 is the same as plus a half. And take the limit. R approaches negative infinity. So we've got to look up at the exponent. R approaches negative infinity. What happens in the exponent here?
All of that will approach it.
R approaches negative infinity. It's getting squared. So now we're approaching positive infinity. And then it gets made negative. Is everybody okay that the exponent approaches negative infinity. E to the negative infinity power is 0. So this guy over here is 0, means the negative 1/2 is what survives. Okay, negative 1/2 plus, now I go over here, s approaches infinity. Hey, you know what? Same story. S is approaching infinity, infinity squared is infinity, make it negative, e to the negative infinity is going to be 0. So we get negative 1/2 plus 1/2, and you get 0. Converges or diverges?
Converges.
Converges. So we just did this integral from negative infinity to infinity, and we get 0. How could that ever happen?
It's,
Oh, it's symmetric.
yeah,
It's
symmetrical.
like an even. It's an even function.
It's not even.
It's
If it was an even function, this wouldn't happen.
odd.
It's an odd function. If you actually went and you graphed x times e to the negative x squared, what you'd see is there's going to be like places where you're like increasing, and on the other side of the y-axis, it's decreasing in exactly the same way. It's an odd function, and odd functions over symmetric limits converge to 0.
Do you have to do all the work to know that?
If you if you knew that, no, you wouldn't have to do that. Okay, pretty good. The quiz thing is an optional